welcome. Today we're going to talk about roots of complex numbers. Okay, so this is the point in the course where we're really going to depart from maybe what our intuition about things has led us to believe. So this time we're going to see some really interesting phenomena happen when we talk about roots. So let's recall, remember what we did with exponents. So exponents, we usually would write z to the n, right, where z is r e to the I theta, and we're able to use the polar form in order to greatly simplify or really clarify what's happening with complex numbers, where r to the n is a real valued exponent, and the angle then rotates n thetas around the unit circle, and it lands somewhere on the space. So for instance, it would go like this. So if your theta was there, and let's say n was 3, then it would just go 1, 2, 3, round to there. And whatever r is, it would maybe extend it or shrink it depending on its magnitude. So z to the n would be there if z was there. Okay, so that's the idea. But now let's see if we can do the same thing with roots. So recall a root. So if I want to talk about z, and I want to talk about its nth root, that is equal to z to the fractional exponent 1 over n. So now I'm going to try the same trick there. So z to the 1 over n is just like any other exponent. Let's try doing that. So that will be r e to the I theta, our representation, all to the 1 over n power, and that becomes r to the 1 over n, and then that becomes e to the I theta divided by n. All right, so now let's draw another axis and let's put our theta value there, let's say. All right, so, and let's say what we're going to, maybe make n is equal to 3 again, right? So we want to make this a third the size. So if I can kind of break it up into thirds there, we can see that it's going, so there's 3 of those. So now we're gonna shrink it by a third. So it's going to bring in, it's going to be taken to a third its value. So it'll be there, let's say. So that would be z to the third. Okay, so so that's an example of what happens visually with roots. But here's the issue here. Recall that we have a multiple angular representations of each z. So for instance, we have z is equal to r e to the I theta, where theta is actually what we call that principal argument of z. And that means it's within the zone pi to negative pi to pi. All right, but there's all these other equivalent versions of z, r e to the I theta, but now I'm going to add plus 2 pi k, where k can now be 0, and that's that principal argument, and also plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 3, and so on to infinity in both directions. These are all multiple versions of the same complex number. So now we have this issue of many to one, right? So if I have a complex number, there it is represented, but then I can also go around the circle once, I can go around the circle twice, and I always end up at the same spot, or I can go in reverse. I can go negative angles. As long as I'm going 2 pi multiples of that angle, so that in this case, there's this principal argument, but then theta plus 2 pi k represents one of the other non-principal arguments of z. Okay, so so this is how we can represent complex numbers. So it turns out this issue, this multiplicity of representations, will hold a really important feature when we talk about roots, because we all know that there may be more than, well, what we're going to find out is there are more than one root for every root available. So now let's go to a new sheet of paper. So now let's talk about that. So again, now we have z, and we're going to represent it in its full multiplicity, e to the r, or r e to the I theta, where the theta is the principal value, plus 2 pi k. All right, we're there. Where k then, of course, is 0, plus or minus 1, plus or minus 2, and so on and so forth. Okay, so with this in mind, now we're going to take z. We're going to take the nth root of z, and that's going to become r 1 over n. And now that's e to the I. We write our theta plus 2 pi k all over n. Now we get r to the 1 over n, e to the I, theta over n, plus 2 pi over n k. Okay, so now we see there's actually many roots available. So let's give an example. So let's try this particular example of, we'll take z to be equal to -1 plus I. Okay, so let's write down what that looks like. So I'll write a little axis here. I'm going to make it more precise, because I want to get my results looking really good. All right, so this number can be represented by square root of 2, right? That's the magnitude of this complex number. E to the I. Now this is going to be 3 pi over 4. Sorry, 3 pi over 4. Okay, so where does that sit on the circle? Well, we'll say this is 1 right there, and that's 1 there. So our complex number is right there, right? And I'm going to put a dotted line going down. So that is -1 plus I, and that angle there is going to be 3 pi over 4. Okay. So now the question then is, where I'm actually going to rewrite where the position of that is. I'm going to put that 3 pi over 4 there. So now let's try z to the third root. Okay, we're going to take the third root of z. In this case, that's going to be 2 to the 1/2 power, all to the 1/3 power. But now we have to rewrite this formula. Sorry, I'm going to redo this in the other line. We have to also put in all those non-principal arguments, 2 pi k, all in there. So in this case, that becomes 2 to the 1/2 to the 1/3, e to the I, 3 pi over 4 plus 2 pi k, all over 3. Okay, so this becomes 2 to the 1/6, and that becomes e to the I. And we see the 3's cancel there, so we're left with a pi over 4 plus a 2 pi over 3 k. And again, k goes from 0, plus or minus 1, and so on and so forth. I'm gonna erase that there for now. Okay, so this number here, I mean, let's not make too big a deal out of that, but that's about about 1.225. Okay, about that. Okay, and now let's see where this goes. So now when k is equal to 0, that's going to be pi over 4. So we see that the principal root, so when k is equal to 0, what we get is z to the third is going to be 2 to the 1/6 e to the I pi over 4. And I'm going to call this right here the principal root. And that's the root where k is equal to 0. Okay, we define the principal root to be that root. It's the root where we don't have to worry about any of these multiplicities that happen there. All right, and so that pi over 4 lands right about there. So square root of 2, that's 1.41 about. We want to go out to 1.2, so it's a little shorter. And now it's at pi over 4. Okay, looking good. But now let's talk about some of those other roots. So let's talk about z. One of the other roots is z is equal to 2 to the 1/6 e to the I pi over 4 plus 2 pi over 3. Right, so what's 2 pi over 3? The angle, it's a third of it's about a third of the way around the circle, so it's about right there. So now we have another root. So what we've done here is we've gone from here to there, and that's 2 pi over 3 angles. Starting from there, so we started from pi over 4 right there, and we've added 2 pi over 3 to get to there. And now, so that was for k is equal to 1, but now k is equal to 2. We have z is equal to 2 to the 1/6 e to the I pi over 4 plus 4 pi over 3. Okay, and so that's another 2 pi over 3, and that goes around to about there. And now if I go to k equals 3, you see I've actually gone back over to this one right there. So we see that there are actually now, so we don't have to worry about that one. So these are the 3 roots. So we see that this is the principal root. And then there's these 2 other auxiliary roots. So when we talk about principal roots, I don't, whatever you want to call these, are just auxiliary roots, these additional roots. So in total, there are, for n equals 3, it implies then that there are 3 roots for z to the n. Okay, so now we see that when we take a root, we get 3 different values for it for n equals 3. And of course, you can expect then for any other n, we're going to have n roots, including 1 principal root. All right, so let's try another example. And we'll go back to something now that's maybe a little bit simpler. See if we can get an idea of what's going on here. So let's try z is equal to, z is equal to 4. All right, so that's a pretty simple complex number. I'm going to say that that's 4 then, e to the I, and we usually write it as 0 because we're right on the x-axis, but we're going to put, again, that 2 pi k. So another way to write that is 4 e to the I 2 pi k, where k, again, is 0, plus or minus 1, and so on and so forth. All right, so now let's try doing something really simple, which is just take the square root. Okay, and we all know intuitively that the square root of 4 is, of course, 2. But this doesn't jive. There should be, again, so we would think that this is the principal root. But, where's the other? Where's the other root? So let's see if we can go through this a little bit more systematically. So again, now we're going to take z to the 1/2 is going to be equal to e. It's going to be equal to 4 to the 1/2. e to the I 2 pi over 2 pi k divided by 2. And that's going to be, well, that of course is our principal root, 2 e to the I pi k. All right. All right, so where is that other root? We can see that for k is equal to 0, we get the principal root equal to 2. And then now k is equal to 1. We see we get 2 e to the I pi, which of course is negative 2. What about k is equal to negative 1? Well, we get 2 e to the negative I pi, which is also negative 2. All right, so that looks good. What about k is equal to 2? Well, that's going to be 2 e to the I 2 pi, which is again back to 2. So we see that the roots to root 4 is going to be plus or minus 2, which is a familiar result. And this is the two roots in the complex plane now. All right, so again, we write that as follows. If I want to draw this axis, this is the complex plane. There's 4, there's 2. So, but then the two roots then are, of course, at plus or minus 2. Okay. So now let's try yet another example, something a little bit more, maybe a little bit more interesting. Let's try doing the same thing. We're going to take now the square root of I. Okay, so that's going to be I to the 1/2, and I we can write as e to the I pi over 2, but that's the principal root, or the principal value of the principal argument. We have to include also all the additional multiplicities there. And now we're going to take that all to the 1/2. And that becomes e to the I that becomes e to the I pi over 4 plus pi k. All right, so this is pretty interesting now. So let's see if we can get an idea of what that looks like again. So I'll write out my axes, and I'll put down, here's I right up there. All right, and that of course is going to be pi over 2 angle. And now we see that we're going to pi over 4. All right, and then now we're going to go add multiples of pi to this. So our root goes around like that. That's for k is equal to 1. So we have another root over here. So this is again the principal root. And there is the auxiliary root on the other side. And so we can write this now as e to the I pi over 4. And then I can kind of put this off to the side now, this e to the I pi k. And we notice that if k, so that's for k is equal to 1, but now when k is equal to 2, we go back over to there. So that's k equals 2. So k equals 2 is kind of redundant. We don't need any other value there. So really all we need is k is equal to 0 and k is equal to 1. Those are the only two that matter in terms of the roots. So we see that this then represents a nice way, a compact way to write our two different roots. All right, so let's see if we can get even more perspective on this. Let's now start taking roots. Now let's do roots of 1. All right, so this is probably the most boring number of all, or if you think, might be the most exciting one, depending on your perspective. But the idea here is now let's do, so of course, 1 to the 1/2, that's going to be, so 1, or sorry, is going to be e to the I 2 pi k divided by 2, and that's going to be equal to e to the I pi k. So of course that's equal to plus or minus 1. Okay, now 1 to the 1/3, that becomes e to the I So I'm going to draw that up here. I'm going to draw a little axis. Oops, it's not the best axis I can draw. We see the two roots to that are, of course, 1 and minus 1. Now e to the I 2 pi k, and we're going to divide by 3 now, right? And that's going to be, if I can draw a picture of that, we always get that root. So when k is equal to 0, we get the principal root of just 1. But now we see there's two others. We get another one at 2 pi over 3 right there. And we get another one at 4 pi over 3. So you can see that draws a nice equilateral triangle. And there's another 2 pi over 3 going back. So there's an equilateral triangle like that. This should be straight up and down. There it is. That looks a little bit better. Right about there. Okay, so of course we can do the same thing for the fourth root of 1. That's going to be e to the I 2 pi k over 4, or rather e to the I pi over 2 k. And now you can see that there's a nice pattern here. Here there was 3 roots that are 2 pi over 3 rotations around the plane. And now we see we have pi over 2 rotations around the plane. So we go from here to pi over 2 to pi, and then also back to 3 pi over 2, and then finally back there. All right. So now we see a nice pattern growing here. And so now we see a really kind of a nifty way to represent roots of complex numbers. So let's talk about now this next one here. So we notice that for 1 to the nth root, all of them can be written as follows: e to the I 2 pi k over n. And that's actually equal to then, of course, 1. And that's also equal to e to the I 2 pi over n. All right, and then there's also e to the I 4 pi over n, e to the I 6 pi over n, and so on, all the way to e. Should just put a comma there. All the way to e to the I 2 pi over n times n minus 1. Because when we get to n, we've gone all the way around the circle. So we only want to go just up to that point, because that'll be equivalent to going back to 1. So in fact, I can define this as 1 to the 1nth power is actually, I can call this now a set, which I'm going to call omega n k, where k goes from 0 all the way to n minus 1, and the omega n k's are equal to e to the I 2 pi over n times k. Okay, so these turn out to be really important components to creating these roots of complex numbers. If I have z and I want to take to the 1nth power, or to the nth root, I can write the principal root. So I can talk about, I can go r e to the I theta over n, 1 over n, where theta is going to be that principal argument of z. And I can multiply, to get all the other roots, I just have to multiply these omegas to it to get all the other roots. So of course I can get k is equal 0, that's the principal root, but also 1, 2, 3, 4, all the way up to n minus 1. So this is a nice way to write, a good representation to write any root you can, or you want to write for these things. But okay, so the big picture here, Zn has n distinct roots, and they can be and they sort of fan out over the plane in 2 pi over n increments. All right, and that's exactly this thing right there. Wherever you are, you're going to go around n times till you get back to where you started. Okay, and that's the idea, is that these 2 pi over n increments move you around the plane till you get back to where you started. All right, so thank you very much.